Since they were first developed back in the 1930s, synthetic polymers, what we commonly call plastics, have revolutionized modern society. They can be found everywhere, from packaging and consumer goods to even the most challenging engineering applications. Their unique molecular structure is what makes polymers so special. It determines all of their macroscopic properties, like how they behave at different temperatures and how they respond to applied stress. Understanding this structure is the key to mastering polymers, so that's where we'll start. A polymer is a material made up of a collection of extremely long molecules, each of which is formed from a repeating pattern of a smaller molecular unit. The repeating unit is called a mer, the Greek word for part, and it's the fundamental building block of any polymer, which means multiple parts. The polymer shown here is polyethylene, probably the most widely used of all synthetic polymers. Its repeating mer unit has 2 carbon atoms and 4 hydrogen atoms. Linking all of these mers together creates a long molecular chain that has a backbone of carbon atoms joined together by single covalent bonds, and side groups, which in the case of polyethylene, are all single hydrogen atoms. One polymer chain can contain hundreds of thousands of mers, and there might be 10 quintillion chains in a single gram of material. That's a 1 followed by 19 zeros. The structure of a polymer can be represented by showing the mer chemical structure enclosed in square brackets, and using the subscript N to indicate that the unit is repeated. Here we can see polyethylene with its repeating mer unit consisting of carbon and hydrogen atoms. Polypropylene has a similar structure to polyethylene, but with a CH3 side group. Polyvinyl chloride has a chlorine atom side group. PTFE, also called Teflon, has fluorine atom side groups. And polystyrene has a benzene ring side group. These are just a few examples. Although synthetic polymers have backbones consisting mainly of carbon atoms, there's remarkable diversity in the number of atoms in the backbone and the size, shape, and composition of the side groups. These variations account for the hugely diverse physical, chemical, and mechanical properties of polymers. And as we'll soon see, several other factors influence those properties too, meaning even 2 polymers with the exact same chemical structure can have very different properties. The long molecular chains that make up a polymer are formed through a process called polymerization, where precursor molecules called monomers that each consist of a single mer unit are assembled to form polymer chains. PVC, for instance, is produced by polymerization of the gas vinyl chloride. And polyethylene is produced by polymerization of ethylene gas. Like most synthetic polymers, the ethylene and vinyl chloride monomers are derived from non-renewable hydrocarbon sources. Some are made from renewable resources though, like PLA, polylactic acid, which is commonly used as filament in 3D printing. Its monomer is lactic acid, which can be obtained from fermented plant starch. Some polymers are made by polymerization of several different monomers, all joined together in the same polymer chain. These are called copolymers. ABS, the polymer Lego bricks are made from, is an example of a copolymer. It's formed by polymerization of 3 monomers: acrylonitrile, butadiene, and styrene. There are 2 main ways in which polymerization, the assembly of the long polymer chains, can occur: addition polymerization and condensation polymerization. Addition polymerization begins when an initiator is added to the monomer mixture. Under specific temperature and pressure conditions, the initiator breaks down, generating 2 highly reactive free radicals with unpaired electrons. These free radicals react with the monomers, breaking their carbon-carbon double bonds and forming new covalent bonds. This creates a new reactive site on the monomer, triggering a chain reaction where nearby monomers open their double bonds and attach themselves to the growing polymer chain. The chain continues to grow until either the supply of monomers is depleted or the process is deliberately terminated by applying inhibitor agents. Condensation polymerization works very differently. In most cases, it involves two different monomers. These monomers have complementary functional groups, which react together, forming covalent bonds and releasing water molecules or other byproducts in the process. These reactions continue, with chains linking together end to end, gradually building long polymer chains through repeated condensation reactions. Unlike addition polymerization, which is a chain growth process, where each polymer chain can only grow by one monomer at a time, condensation polymerization is a step growth process. Individual chains of any length can react with each other to create longer chains. Polymers usually have a dominant structure type, depending on the polymerization conditions and the monomer involved. This affects how the polymer chains interact with each other, and plays a key role in determining the polymer's properties. In a linear arrangement, the polymer chains are continuous lines, with each mer in the chain only being connected to two other mers. The chains are held together by relatively weak intermolecular forces. In a branched arrangement, the chains are held together by the same weak intermolecular forces, but the main backbone of each chain can have side chains attached to it. And in cross-linked arrangements, strong covalent bonds are formed between different polymer chains. This creates a rigid three-dimensional network that's very structurally different to the linear or branched arrangements. High-density polyethylene and PVC are examples of polymers with linear structures. Low-density polyethylene has a branched structure, and vulcanized rubbers have a cross-linked structure, as we'll see in more detail later. When linear or branched polymers are heated, the weak intermolecular forces holding the chains together break down easily, allowing the chains to move relative to one another. This is the polymer melting into liquid form. This category of polymers is called thermoplastics. These polymers are usually what we mean when we refer to plastic in everyday life. Thermoplastics are widely used in manufacturing because they can be heated and reshaped through processes like injection molding. But this also means they don't perform well at high temperatures. Cross-linked polymers behave very differently. The cross-links, strong covalent bonds between polymer chains, limit relative movement of the chains when heated. These materials are called thermosets. They don't melt, and instead just decompose when covalent bonds begin to break at high temperatures. They're commonly used in adhesives and in composites, like the epoxy resins in carbon fiber reinforced polymers. Thermosets often start as prepolymers, liquid resins that contain partially polymerized chains. They're transformed into a rigid material through a curing process, where heat or a catalyst are applied, triggering chemical reactions that form the cross-links between polymer chains. Unlike metals that have a very regular crystalline structure, most polymers are semi-crystalline, meaning they contain both amorphous regions, where the polymer chains are randomly jumbled together, and crystalline regions, where they align in a very regular pattern that allows them to pack together very closely. These crystalline regions often form spherulites, spherical regions of highly ordered chains that grow outward from a central nucleation point when cooling from the melt. Linear polymers with small symmetric mers tend to have the highest degree of crystallinity because these characteristics allow chains to pack together very closely. Branched polymers, or those with other features that prevent close packing, like bulky side groups or irregular mers, tend to be much less crystalline. And some polymers that have very bulky or reactive side groups are completely amorphous, because the side groups completely prevent polymer chains from arranging themselves into an ordered structure. This is also true of cross-linked polymers, because cross-linking prevents polymer chains from forming ordered structures. Polymers with a high degree of crystallinity tend to be stiffer, stronger, and have a higher melting point than more amorphous polymers, because close packing creates stronger intermolecular forces. High-density polyethylene has linear chains with minimal branching, with crystallinity of around 80%, whereas low-density polyethylene has a branched structure resulting in much lower crystallinity of around 40%. The difference in crystallinity explains why the two materials have significant differences in stiffness, strength, melting temperature, and density, despite being made from the same repeating MER unit. Even optical properties are affected by crystallinity. Crystalline regions tend to scatter light, so more amorphous polymers will generally be more transparent. PMMA, also called plexiglass or perspex, is transparent on account of its amorphous structure. To be able to use polymers effectively, it's important to understand their mechanical properties. Let's start by looking at two key properties: stiffness and strength. When plotting stiffness and strength against density for polymer, metal, ceramic, and composite materials, polymers are clearly clustered in the lower left region of the graphs. They have low stiffness, with Young's modulus values maxing out at around 4 gigapascals, which is 50 times less than steel. This is down to the intermolecular forces holding polymer molecules together being a lot weaker than the metallic and covalent bonds found in metals and ceramics. Polymers also have relatively low strength, with ultimate strengths ranging from 10 to just over 100 megapascals. One of the big advantages of polymers is their lightweight. Their low densities make them valuable in so many different applications, even if they might not have exceptional stiffness or strength. Some high-performance polymers, like polyether ether ketone and polyethyramide, which goes by the brand name Ultem, have ultimate strengths that are very respectable when considering their low densities. These materials are often used in demanding applications that require lightweight parts, like in the automotive or aerospace sectors. Polymers can offer a range of other useful characteristics too, like excellent corrosion resistance, excellent electrical and thermal insulation, and low cost. Plus, they can easily be mass-produced using manufacturing processes like injection molding. One unique group of polymers is elastomers. These materials have very low stiffness and can stretch to several times their original length without permanent deformation. Natural rubber, called latex, is a well-known elastomer. It can stretch elastically to strains over 500%, but is actually quite weak in its natural form because its polymer chains are mainly held together by physical entanglements and weak intermolecular forces. This makes the material easy to deform, but limits its strength and durability. A process called vulcanization can be used to improve the properties of natural or synthetic elastomers. It involves heating rubber in the presence of sulfur, which forms crosslinks between the polymer chains. These crosslinks significantly improve the rubber's strength and wear resistance by forming anchor points that prevent the polymer chains from sliding past each other irreversibly during deformation, and help the material return to its original shape when the load is removed. The density of these crosslinks is important. Enough are needed to prevent polymer chains from sliding past each other irreversibly, but too many, and the material will behave like a thermoset, becoming brittle and unable to stretch without breaking. Vulcanization and other methods of cross-linking are typically required for elastomers used in demanding applications, like gaskets and tires, to enhance their strength, elasticity, and durability. To better understand the mechanical properties of polymers, let's take a look at some typical stress-strain curves. Polymers can exhibit either brittle or ductile behaviors. Thermosets, like epoxy resins, and some thermoplastics, like PMMA, tend to behave as brittle materials at room temperature. They fracture suddenly at relatively low strains. Many other thermoplastics, however, exhibit ductile behavior at room temperature, undergoing significant plastic deformation before fracture. Polyethylene, polypropylene, and nylon are all ductile at room temperature. Elastomers like latex and neoprene are extremely ductile and can stretch to very large strains before breaking. The ability of polymer chains to move relative to one another plays a key role in determining whether a polymer behaves in a ductile or brittle manner at room temperature. Molecular structures that restrict the motion of polymer chains, like those with highly crystalline regions or extensive cross-linking, tend to be brittle. PMMA has bulky side groups, which contributes to its tendency to fracture in a brittle way at room temperature. When a ductile metal is subjected to a tensile load, it will eventually reach the yield point, where it begins to deform plastically. Beyond this point, a localized weak area forms, in a process known as necking. All subsequent deformation occurs in the region of the neck, eventually leading to fracture. Ductile polymers behave differently. A neck forms at the onset of yielding in a similar way, but the behavior after necking is different because the material undergoes a process called cold drawing, where the applied load causes the polymer chains to gradually align along the direction of applied stress. This realignment of the polymer chains strengthens the material and causes the neck to propagate along the full length of the specimen, instead of all deformation being fed into a single location. As the load continues to increase, the polymer will eventually fracture. This cold drawing behavior is sometimes used to intentionally strengthen polymers. Kevlar is a polymer made of fibers that are mechanically drawn to align their polymer chains, resulting in a material with exceptional tensile strength along the fiber axis. Unlike ductile polymers, brittle polymers fail with very little plastic deformation. Instead of stretching, they fracture suddenly at low strains. A unique phenomenon associated with the failure of brittle polymers is crazing, where a network of fine, linear features form within the polymer just before fracture. These features are tiny voids within the polymer, but unlike cracks, the voids are bridged by fibrils of polymer material. These fibrils are load-bearing, and they absorb energy, which delays crack formation and propagation. If the stress continues to increase, these crazes can grow into full cracks, leading to failure. It's usually difficult to visually identify the onset of brittle failure, because it happens so suddenly. But crazing can give an early indication that catastrophic failure may be imminent. Strength, stiffness, and other mechanical properties of polymers can vary a lot with temperature. Polymers tend to be relatively brittle at low temperatures, becoming much more compliant and ductile as temperature increases. Let's look in more detail at how Young's modulus changes with temperature for a typical semi-crystalline thermoplastic. At low temperatures, the material's stiffness is relatively high and stable, but as temperature increases above a certain threshold, it suddenly drops. Keep increasing temperature, and eventually the thermoplastic melts to a liquid, and the stiffness decreases to zero. This graph shows three distinct mechanical behaviors, which are driven by how amorphous regions of the semi-crystalline polymer respond to temperature. At low temperatures, the thermal energy is too low to allow the chains to move much relative to each other, so intermolecular forces and the physical entanglement of the polymer chains keep everything locked together. The result is a material that behaves as a hard, stiff, and often brittle solid. As temperature increases, the thermal energy is large enough to overcome the weak intermolecular forces that hold together the amorphous regions of the polymer. Although the closely packed crystalline regions are unaffected, the increased mobility of the amorphous regions makes the material much more flexible. The temperature at which the polymer transitions from a stiff material to a more compliant and often more ductile one is called the glass transition temperature, TG, although it actually occurs over a range of temperatures. At sufficiently high temperatures, the crystalline regions of the material lose their ordered structure, which transforms the ductile material into a liquid. This change occurs at the melting temperature, Tm. Amorphous polymers have no ordered crystalline regions to hold everything together, so they tend to soften gradually above Tg, instead of having a well-defined melting point. And thermosets, with their rigid cross-linked structure, don't have a melting point at all. Anything that restricts the mobility of polymer chains increases the glass transition temperature. Significant cross-linking, bulky side groups, or very long polymer chains that are more entangled all restrict motion, resulting in higher glass transition temperatures. High-density polyethylene, for example, has a glass transition temperature of -90 degrees, making it flexible at room temperature. Its relatively simple monomer and linear structure mean its molecular chains can move past each other easily, requiring less thermal energy to become mobile, hence the low glass transition temperature. Here are the glass transition and melting temperatures for a few other commonly used polymers. Amorphous polymers like PMMA and polycarbonate often have high glass transition temperatures, meaning they have high stiffness at room temperature. Their irregular, tangled chains restrict motion, and they're more likely to have bulky side groups, which also limit chain mobility. The glass transition temperature of some polymers can be reduced with the use of additives called plasticizers, small molecules that insert themselves between polymer chains to reduce intermolecular forces. Unplasticized PVC is rigid at room temperature, making it suitable for applications like window frames and pipes. But incorporating plasticizers reduces the glass transition temperature of PVC to below zero, producing a material that's flexible at room temperature and can be used for things like wiring insulation or flexible tubing. The glass transition is such an important factor to consider when working with polymers. This was tragically demonstrated by the Challenger Space Shuttle disaster, where cold outdoor temperatures on the day of the launch caused the elastomeric O-rings on the solid rocket booster to lose some of their flexibility. This prevented them from maintaining a proper seal, and contributed to the catastrophic failure of the shuttle. The temperature sensitivity of polymers has a lot of implications. It affects the extent to which a polymer exhibits viscoelasticity, for example, a curious mechanical behavior where a material behaves partly like a solid and partly like a viscous liquid that flows over time. But that's a topic that deserves its own video. It also impacts manufacturing. The generation of excessive heat during machining, for example, can lead to material softening and a loss of dimensional accuracy. Producing high-quality polymer parts is a challenge and involves a lot of nuance, and that's why I'm excited to introduce you to this video sponsor, Protolabs. Protolabs is an innovative digital manufacturing company that provides manufacturing services throughout every phase of the product lifecycle, from custom prototyping to full-scale production. I've used them professionally on several occasions, and have always been very impressed with the quality of the product and their fast turnaround times. Their whole operation is optimized for speed, and they can produce parts in as little as one day, which is amazing for rapid design iteration. Protolabs offers 4 core services: 3D printing, CNC machining, injection molding, and sheet metal, and it's really easy to get started. Just choose a service, upload your CAD file, and select a material. Their instant quoting system will give you a quote straight away, so you immediately have a clear picture of production costs. The quoting system even includes a real-time design for manufacturability tool to help you catch potential production issues before they become a problem, so you can be sure your design is production ready and avoid costly revisions and lost time. Protolabs offers hundreds of different materials, from everyday polymers like ABS and Nylon 6,6, to specialist engineering materials like PEEK or ultra-high molecular weight polyethylene. And it's not just polymers. They have a wide range of metals too, including aluminum and titanium alloys, steels, and even high-performance superalloys like Inconel. And with the Protolabs team of expert engineers ready to provide support at every stage of the process, transforming innovative engineering ideas into high-quality physical products has never been easier or faster. Whether it's a prototype of a complex machined assembly or a production run of injection molded parts, Protolabs could be the perfect manufacturing partner for your engineering project. Just click the link in the description to visit Protolabs and get an instant quote today. And that's it for this look at polymers. Thanks for watching.